Okay, thank you. I was just waiting for the slides to start there. I'm Kenny Wood from University of St Andrews, but I'm really giving this talk on behalf of a large multidisciplinary, interdisciplinary team that we assembled over the last 3 years. And this is just some of the organisations that we've been working together on the topic of Far-UVC. And we've all come to this as somewhat sceptical scientists. We heard some of the hype about how the Far-UVC can inactivate pathogens in the air and on surfaces. It's got low ozone and it's safe because the light can't penetrate through skin. So we came into this asking, is this really true? And the questions we wanted to ask is it safe and does it work? So I think that's what most people in this room are wanting to know as well. The first part that we started working on was skin safety studies. And I'm taking you back now to a paper from 2015 by Julie Woods and a team from Ninewells Hospital in Dundee, and some of the people are in this audience that have worked on this paper. And what they did was, it was a dose escalation study using unfiltered krypton chloride light. And they had 4 volunteers and they were exposed. It was meant to be a dose escalation study, but after they got to 50 millijoules per square centimetre, all of the subjects presented with erythema. And they also, through the punch biopsies, they found that there was CPD formation or DNA damage going all the way down to the basal layer. So the study was then stopped. And that's sort of where it lay until my colleague Ewan Eadie contacted me it was actually the day that lockdown was announced in the UK by the British Prime Minister at the time. And he said, let's go back to this and have a look at it and use some of the computer models that we've been using in our other research to see if we can understand which wavelengths in this unfiltered krypton chloride spectrum were producing the DNA damage. And that's then what we did. So using Monte Carlo radiation transfer simulations, that just tells us how the light propagates through a 3-dimensional skin model that we'd made up with different layers for the skin and different optical properties in each layer, representing the stratum corneum, the epidermis, all the way down to the basal layer, and then into the dermis itself. And on this image on the left here, we're showing the thickness of the skin. Now it's on a log plot because we want to show how deep the light is getting down into the skin. And the lines are showing different percentages of how much of the incident light as a function of wavelength is able to penetrate into the skin model. So when we're down at 200 nanometers, very, very little light at all. In fact, essentially 0 is getting through the stratum corneum. And this is due to absorption by proteins in the uppermost layer, the dead layer of the skin. So we then took the Monte Carlo model and then folded it through with the unfiltered krypton chloride spectrum, and we could see how much light was getting to different layers in the skin, going from the upper epidermis and then all the way down to the basal layer. And we found that when at 220 nanometers, even out to 235 nanometers, you're essentially getting no light at all is getting down to the basal layer. That's important because that's where any DNA damage that happens there can then replicate and potentially develop into cancers. We also folded it through with a CPD action spectrum. And the result of our work was what we're driven to is that the DNA damage and that the erythema that was produced must have come from the longer wavelengths that were present in this spectrum of the unfiltered krypton chloride light. So that's why you've heard a lot today about filtered lights, and you'll hear throughout the conference and why filtering is so important. So if you can somehow reduce the intensity of this long wavelength emission, then you're not going to be producing erythema or DNA damage. So based on that, my colleague Ewan Eadie then decided to do a trial on himself, and as Sally Ibbotson as well. And I asked him, why on earth did you do this, Ewan? Why did you expose yourself to such large doses of UVC light? And he told me that he trusted my models. Yeah. And I can see Ewan sitting here. Can you maybe hold your arms up, Ewan? Yeah. Because those are the arms that were exposed to over 6,000 millijoules per square centimetre. So following on from the computer simulations, Ewan then heroically exposed his arm. And actually the referee's report on the paper did use the phrase heroic in the report. Exposed his arm, and then there was some punch biopsies done, and you can see that there is this staining here is due to some DNA damage, but the important thing is it's just below the stratum corneum. So it's in the layers of the skin that are no longer replicating, and they're on their way to being sloughed off. Okay, so that was just one particular skin model, one particular skin type, and we've been asked over the years, well, what about very thin stratum corneums? What about older people? What about younger people? What about different skin types, different melanin contents? And our student at St Andrews has been working over the last few months on extending the computer simulations that I just showed, but to look at exactly this. Different skin types, different aging effects. And what Anna then did, she went through the literature and found out, how does the skin change with age? And the epidermis thickness decreases as you go from a 30-year-old to an 80-year-old. So we wanted to fold that into our Monte Carlo simulation. And then also, what's the melanin fraction? How does that, or the melanin volume content, how does that change with age? And then also for different skin types, going from the darkest, skin type 6, to the lightest skins, skin type 1 and 2. And the overall results are, again, very encouraging for Far-UVC, is that, again, due to the protection of the stratum corneum, but then also, as David Brenner mentioned earlier, Far-UVC light doesn't penetrate very far in biological tissues in general. So this is the results from some of the simulations that Anna has been running. Nothing changes in the stratum corneum because we kept the thickness of the stratum corneum the same as a function of age, but I'll show some other results in a minute or two. And this is a spectrum going from 200 nanometers out to 300 nanometers. And the kind of purple, the blue line here, this is for the middle of the epidermis. And then the purple line is what light is getting down to the basal layer. And you can see even at 80 years old, when you're going to have less protection because you've got a thinner epidermis, no light below 230 nanometers is able to penetrate down. So that's the effect of aging on the computer model's predictions for the effect of aging. And then what about the thickness of the stratum corneum? So we took a model for someone that was at 80 years of age, so that a particular thickness for the epidermis. And then we looked at having stratum corneum thicknesses of 0, 10, 15, and 20 microns. Typical thickness of a stratum corneum is about 15 microns. And again, very little light is able to get down, and this is to the case of the middle of the epidermis. So it seems that overall, changing age and also changing the thickness of the epidermis of the stratum corneum is not going to affect the penetration of Far-UVC light down into the basal cell layers. Now, what about different skin types? So what we did now with the computer model for the Monte Carlo simulation, we introduced different amounts of melanin going from skin type 1 out to skin type 6, and that was distributed just above the basal layer and then also throughout the epidermis is how it was distributed in the model. And again, it's looking very, very good for Far-UVC light, is that going from type 1, so the fairest type of skin, down to type 6, again, no light is getting down to that's the epidermis, and nothing's getting down to the basal layer below 240 nanometers. And as you would expect, people with high melanin content, skin type 6, are going to be the most protected. So the least amount of light is getting down there. And Ewan published a paper a couple of years ago taking results. Again, this is a modeling, taking results from the skin models and saying, we know how much CPD damage comes from sun exposure. So if you were to expose yourself to 10 minutes of the sun in Greece or in southern England, how much time would you need to sit under a Far-UVC light to get the same amount of DNA damage down in the basal layer? And it would be almost 5 years of continuous exposure to a Far-UVC light. And the damage that would be coming, that would be being produced there, it's coming from the longer wavelength emissions. So even though it's filtered, some of that light can still get down, but it would take over 5 years before you would get the equivalent of sitting in the sun for 10 minutes in Greece. Now, this isn't a modelling study, but I just wanted to do a plug for it. We've also been doing some eye safety study work at St Andrews, and we had a pilot study, and the question was, does Far-UVC cause any irritation or discomfort when it's deployed in a room? And we had 37 participants, and they were exposed to different levels of Far-UVC light in a classroom over 6 hours in the day. There was a sham day as well. And the overall result, and this has just been published recently, that there was no significant immediate or delayed discomfort. And this was all done, the eyes weren't examined at all. It was all done through some standard questionnaires for eye discomfort. Okay, going to shift now into the second part of my talk, which was, first part was safety, and now looking at efficacy from the modelling. And these are results from the Columbia desktop size chamber experiments that they were doing, looking at the inactivation of Staph aureus. And that's important because some of the experiments we do at Leeds have been using Staph aureus and then different coronaviruses. So from this, we can determine what the susceptibility is for the viruses when they're exposed to Far-UVC light, because you've got a dose response curve here. And then what we did was we took some computer models for computational fluid dynamics, and we would calculate steady state airflow patterns within, it's actually the same classroom at the University of St Andrews that has some ventilation. So we get the airflow, and then we can put in simulated ultraviolet Far-UVC lighting within this room. And the spaghetti plots that I'm showing here are the paths that particles would take within this simulation. And they start off yellow. That means the particles are active and could be infectious. And as they move through the ultraviolet light pattern, they pick up more inactivation because of they're picking up dose as they're moving around the room. So they go from yellow to purple. So we did some whole room computer simulations for that. And where have we got to as of a couple of years ago? Well, there's rapid inactivation of pathogens within the small chamber experiments. And we've heard a lot today about inactivation of pathogens on surfaces and an aqueous solution. And also from some of the simulations that we did of airflow, UVC light distribution, and inactivation, it's indicating that Far-UVC could be a very promising technology for inactivating airborne pathogens. But this was all in either 30 centimetre size boxes, or it's in my computer. We wanted to know what's it like in real world deployments, and we're starting to see some of that data coming in now. We were lucky to get funding from the United Kingdom Health Security Agency and then also the National Health Service in Scotland. And we got some Far-UVC lights and we took them down to the bioaerosol chamber at the University of Leeds. And this from the first talk in the previous session, the one that was given remotely, this is the setup of the Leeds bioaerosol chamber. So it's a 32 metre cubed room, roughly 4 by 3 and a bit by 2 and a bit meters tall. And we deployed 5 lights, and we could have either the central light on or all 5 lights on. And we could have different ventilation regimes going from high to low, or going from low to high ventilation regimes. Throughout the experiments, we had a continuous injection of the pathogen. So the experiments and the results that I'm showing and then the modelling we've tried to do, it's not for any a decay experiment. It's not like you filled the room with virus and then saw how quickly the lights would inactivate that virus. We're continually bringing in pathogen at a source, and then the air sampling was done as it was described in Wasim's talk. So the experiments ran for 3 hours. The first hour, we didn't take any data. The second hour, by that time, the pathogen load is built up more or less to a steady state. And there was air sampling done, and Wasim also did some surface sampling. And then the lights were turned on after 2 hours. Pathogen is still being injected into the room, remember, and then it settles down to a new steady state. So these were the results. This is like the wake-up slide that we've had for the last couple of years. And if you want to know how many Scotsmen it takes to change a Far-UVC light bulb, there's your answer there. That's the 2 hours. And we did have to change 1 or 2. Okay, so at the current, the exposure limits in Europe, we were getting a 92% reduction of the Staph aureus, and that's when 5 lights were on and deployed at full power. Okay? No, sorry, that's when the 5 lights were on and deployed at the ICNIRP exposure limit. So a 92% reduction. And then it remains at that 92% lower than what it was before the lights turned on. And then with the new ACGI skin limit, roughly that's what the deployment would give at a height of about 1.8 meters in the room. We're getting over 98% reduction. So this was corresponding to equivalent air changes of 34 air changes or over 200 equivalent air changes per hour. Now, where does this come from? I think the PDFs of the talks are going to be made available. So I've made sure that I've got all the equations in here, because I'm now going to get into, this is like a UVC anonymous session, because I don't understand the data or the models. We're not able to explain this. So I'm now looking for your help. I'm going to talk you through the problem or the conundrum that we've come up to. So this is equation for a well-mixed room, the pathogen creation, sorry, the rate of change of active pathogen is going to be the creation, so that's a continuous injection, minus the removal. So you've got removal by ventilation, which is this term here, and then you can also have removal, which means just inactivating the pathogen due to the ultraviolet lights. That has a general solution. It's a nice analytic solution for this differential equation. And then you can get a ratio for the steady state concentration when the lights are on compared to when the lights are off. And from that, you can express this in terms of the air change rate due to the ventilation, and then the equivalent air change rate, which is going to be air change rate due to the ventilation, plus this additional term due to the germicidal ultraviolet lights. And here's a solution for this differential equation, where I keep the pathogen being injected into the room continuously throughout the time interval on the x-axis here. And then after 2 hours, so I keep it at 3 air changes per hour up until 2 hours, which is what we have in the Leeds chamber for this set of experiments. And then we turn no lights being turned on in this. I just changed the ventilation rate to be 37 air changes per hour. So that's what's needed to take you from this level down to 8% of that level, which is what we noted. And that is where we get the equivalent air change rate of 34 air changes per hour. So I just wanted to go through that carefully. We were then able to do the computer modeling for this. Now just bear with me for a few slides. And we looked like we were successfully matching the data from the Leeds chamber for 1 light, for 5 lights, for different ventilation rates. So all the data that Wasim presented a few hours ago in his talk, we thought we were modeling that successfully. Then we got on to looking at ozone production. So we chatted with Jose Jimenez, and we put in within this computer model of the airflow for generating ozone only due to the Far-UVC lights, and then the removal was only due to the ventilation. So this would give an upper limit to how much ozone would be produced in the chamber. And we were making some predictions for how much ozone would happen at the ACGI skin limit, the ICNIRP limits, and then at a very low limit as well. So we're predicting up to 45 parts per billion with these simulations for the highest intensity of the lights. And this was the ozone data that was taken at Leeds fairly recently. So this was shown in Wasim's talk. So initially the lights are off, then the lights get turned on for an air change rate of 1.5 air changes per hour. The ozone builds up. Then the air change rate, the ventilation is changed to 3 air changes per hour. It decreases somewhat the amount of ozone because you've removed ozone due to the higher ventilation rate. So we get this really lovely data set. And the computer models were doing not too bad at reproducing some of this ozone data. Now, here's where I'm being honest now. We had an error in our computer simulations. We had the fluence rate was wrong by a factor of 10. So factor of 10 too high was the fluence rate. When we corrected that error, we found that the computer simulations for the Leeds chamber were matching up very well with the predictions that you would get from a 0D well-mixed model. But they're both under-predicting the amount of inactivation and also under-predicting how much ozone generation we were seeing within this particular chamber. So this is now where I'm asking for the help of the Far-UVC community. What's going on? Can you help us explain this data? Is there a strange airflow pattern in the Leeds chamber, which is maybe taking the pathogen much closer to the lights, so it's getting a much higher dose, and then also for the air producing more ozone? We don't think so, because, as Wasim explained, the changing the ventilation rate from low to high and high to low doesn't seem to be changing the amount of inactivation that we're seeing. Now, I'm originally an astronomer, so I'm using factors of 4 pi all the time. So is there a factor of 4 pi missing somewhere? That's roughly 10 for an astronomer. That would help. Kath Noakes has also pointed out that the Leeds chamber, it's right next to a very busy road, and they're not filtering the air that's coming in the ventilation system. So if we're bringing in some NOx's, that can interact with a Far-UVC photon and lead to production of ozone. Could that then also lead to more pathogen inactivation? Not sure, because we're only producing tens of parts per billion of ozone, but my understanding is that you're needing tens of parts per million to get inactivation, but I may be wrong with that. So here's where I went down a little Far-UVC rabbit hole, and just indulge me for a few slides, please. Could it be that there's some short wavelength emission in the krypton chloride spectrum that hasn't been accounted for in the simulations? So, and what gave me the hint of this? I looked at some data for krypton chloride lights going down below 200 nanometers, and there's some emission at 190 nanometers. Okay, so the Leeds experiments at 3 air changes per hour were producing an additional 40 parts per billion above the background level. So the question that I wondered is, could emission with wavelengths less than 200 nanometers produce significant ozone? The mean free path of a photon at 190 nanometers is about 20 meters. So that's that doesn't matter for atmospheric chemistry, but if you're in a small chamber, yeah, so the 190 nanometer photon is going to be able to pass across the entire chamber. So again, I'm not going to go through any of this, but if you look at it in the PDF, please let me know if I've got an error in any of these equations. You can get down to the steady state concentration, again, the creation minus removal of ozone, and you get down to a steady state concentration for the ozone produced by the 222 nanometer light, and then also, hypothetically, ozone produced by emission with wavelengths less than 200 nanometers. So here, put it in at 190 nanometers. And what's the result of this? In the Leeds chamber, at 3 air changes per hour, we've found that we generated an additional 40 parts per billion of ozone. This is the average fluence rate that we got in the Leeds chamber, and we got that from irradiation measurements that Ewan and myself did a couple of years ago when we were down there, and then we folded those irradiation measurements into Monte Carlo simulations to determine what the actual fluence rate was throughout the chamber. That 0D model that I just had up on the previous slide, that would predict an additional 6 parts per billion due to the deployment of Far-UVC lights with this average intensity or average fluence rate. So to get an additional 35 parts per billion, you would require this amount of flux at 190 nanometers, so only a few percent of the 222 nanometer peak. Okay, just keep me going with this Far-UVC house of cards for a little bit longer. There's another issue. The room scale experiments, both in Leeds and now the new experiments that David mentioned today, and I think Manuel is going to speak about tomorrow for the inactivation of murine virus, they were giving much higher inactivation percentages than came from the small chamber experiments. So there's some difference between the small and the large chamber experiments as well. So I wondered, could it be, and some of the people that were talking earlier today can maybe help us out here, is it protein damage? Once you get down to below 200 nanometers, this curve is still going up on a log scale. So if you're getting if you get 190 nanometer light, could that be even more effective than the 222 for inactivating viruses? But then what about the difference between the small and the large chamber? And this is where I'm getting a wee bit crazy, right? So the light is passing through this quartz window. The way you could potentially explain the difference between the small and the large chamber experiments is if the 190 nanometer doesn't penetrate through into the small chamber because you're irradiating from the outside, but it's going to be in the large chamber because the light is actually in the chamber. So the summary of all this conundrum that I've found myself in for the last half a dozen months or so, you could possibly explain the excess ozone generation within the chamber if there was 190 nanometer emission that was a few percent of the 222 peak. Could that 190 nanometer emission, if it's there, cause some more protein damage? And that was what I said about the small and large chamber discrepancies. So please check my calculations, make any suggestions. This really is a plea for help. Okay, this is where I'm going to finish. Some of the outstanding questions that we're wanting to address further with both modelling and hopefully more chamber experiments at Leeds is more of the in-room photochemistry that we're going to hear a lot more about tomorrow. What are the humidity effects on the UVC, the aerosol fluid? I believe the Columbia team is doing work on that right now. And a big thing that we'd really like to do is short-range inactivation. It's one thing getting what the average pathogen load is within the room reduced, but what happens for me talking to someone that's just a few meters away? Can the Far-UVC lights have any impact on that? And that's something that we can do through both computer modelling, but also we can want to do it in the Leeds chamber, and then just to do more things there. So that's where I'm going to finish. Thank you.
Okay, you gave us a puzzle to solve, huh? Few more, time for a few questions. There's some up here in the front here.
Chris Bowers with Exemer. So when you're calculating these average fluence fields, how are you doing that? Do you have a volumetric grid that you're essentially calculating the fluence field at for each spatial location?
Yes, so we have irradiance measurements throughout the chamber, and then if you're directly below a light, the irradiance equals the fluence rate. So we then know where the lights are, we know the emission pattern from the lights, so we then put that into our Monte Carlo simulation or any ray tracing code, and then we can determine what the fluence rate is, the 3D fluence rate throughout the room.
So you're essentially calculating, you have a 2D plane set somewhere.
I will actually do it with a volume. There's a way you can do it within the Monte Carlo codes where you look at the path length that a photon takes within a cell, and the sum of all the path lengths can convert into a fluence rate. Briefly, Ed.
Yes. Kenny, we talked about this before, I think on a Friday, but between a small chamber and a large chamber, the ray length differs. This may be a similar question that was just asked, but so the UV travels until it's absorbed. So the same source gives you more potential for disinfection in a larger chamber, no?
Yeah, but we've also got the ozone question as well. Why are we getting more ozone production? The only thing that's common to the experiments is the fluence rate.
So Jay will present this tomorrow, but I think we have pretty conclusive evidence that in the usual lamps that I think you're using, the 190 is not the issue. So I'm voting for the 4 pi factor.
Okay.
Yes, I had 2 questions. One about the radiation transport. So your Monte Carlo simulation includes effects of scattering off the walls and back into the mass. Is that right?
Yes. Yeah.
And then in terms of the fluid mechanics, were there any mixing fans in the room, or just the inlet and outlet? The only thing.
Just the inlet.
So did you do any experiments to validate the well mixedness assumption by, say, doping it with CO2 and watching the coast down and measuring the variance in CO2?
Not like for those experiments, but it's a well-established chamber, and I think Kath can address that. They've been doing these types of experiments for other air cleaning devices at Leeds for a couple of decades now. Is that correct, Kath? And the fluid dynamics makes it look like it's well mixed as well. I do not know. Oh, the reason we started with the fluid mechanics is in case the room wasn't homogeneous, but now the corrected fluid mechanics do seem to match up pretty well with the well-mixed 0D simple analytic solution. Can I sit down?
No.
I've just bare dog to you. Come on.
I'm kind of sorry, but at the same time, I want to commend you to come in front of this audience and say, hey,
Well, you told
I
me you
need
couldn't
to-
explain it either. I've communicated with you. You're
I
sitting
would
down,
be
I'm
happy
standing
to
here.
stand next to you on this one. Question, have you tried to simulate starting with an average fluence rate versus the totally resolved and so
Yes,
on? Are
yes.
the results any different? So what I mean is if we calculate with average fluence rates in the future, we should have approximately right results.
Yes.
Thank you.
And more.
Thank you. Thank you for your excellent talk. Appreciate it.
Thank you.
I have a question about the 190 nanometer emission. Is that a proposal that
Well, I saw it in a spectrum, but Jose now says he thinks is that filtered out in some lights, maybe some lights it's not. It was just a spectrum that I saw.
it's very interesting because all of the rare gas halides have two excited states that emit radiation. Virtually all of the emission comes from the lowest excited state known as the B state of the molecule. But theory predicts emission from a higher lying state that known as the D state that should produce photons with about 1 EV higher than the lowest state. So 190 would be about right, but I'm not aware of any spectra that have observed that for krypton chloride. It's certainly known for xenon monofluoride. But anyway, that's about the right spot. So it's very interesting.
Well, I said 190, but just in general, emission below 200. I was just trying to
Okay,
explore
well,
that.
we can certainly look for it. But thank you.
David, you have a couple more.
Is this the prize I get for finishing early? Here's David.
Well, if your results were better, one possibility could be that your light is coming from 5 different sources instead of in the Columbia work, which was coming from one side.
But that should get taken into account with the computer modeling because we put in 5 lights into the computer model.
I thought you said your results were better than what they obtained at Columbia.
Yes.
So you
okay,
have multiple sources coming at the pathogen in the air from foreign.
It's still better.
Oh, was it?
All right, we'll let you off the hook. Thank you so much.